Fine. Let me share the screen. Okay, let's start with Turing's thesis. We have learned three different automata. One is finite, the other one is pushdown, and the last one is Turing machine. As we progress from the finite automata, we understood that certain languages which are not represented, which cannot be represented by finite, could be represented by pushdown automata such as balance constructs. And there were certain languages with more complexity than what can be solved by pushdown automata, which we were able to solve it using the Turing machine. Now, this Turing thesis is based on the mechanical means of computation which can be performed. So, to understand it, any set of steps, for a given problem, you can write a set of computational steps for solving it. That is what you normally call it as an algorithm. So, whenever you have a problem given to us, a project given to us, we try to analyze the whole problem in the first step, and then we break down into smaller computational steps where we try to come up with a solution. And then we optimize the algorithm. That is what you call it as the algorithm. We optimize it so that we get answers out of it. So whenever you talk about a Turing machine, if I could solve by a Turing machine, you will have an algorithm which can be executed by the Turing machine. Now, in last class, while we were discussing about x plus y and then copy of x. Now, what is this all about? It is all about Turing machine as a transducer. Now, what are we defining here? We are defining a function f with a domain D. What do you mean and function f? Function f is something with the input. So you have taken a set of input and returned certain output out of it. So you have a function f which is with domain D, which you call it as Turing computable, which means it can be solved by a Turing machine. Fine. For which there exists some Turing machine where Q is the set of internal states, sigma is the input alphabet, the tape alphabet. For example, when you take A power n, B power n, A is converted to X, B is converted to Y. So A, B, X, and Y becomes the tape alphabet. The input alphabets are A and B alone. And delta, the transition, Q naught, the initial state, blank space, which fills up the cells is square, and then the set of final states. You will have Q naught W, which is you are starting with Q naught and the set of word on multiple transitions, 0 to 1, 0 to more transition. Transition is indicated by a line and a horizontal line. And then the closure is 0 or more transition by the Turing machine M leads to the final state where you get the answer out of it. Fine. So that is the definition for Turing machine as a transducer. Now, this is the example of what we have discussed in yesterday's class. What have we done here? You are supposed to have two positive integers, x and y, and your Turing machine computes x and y. So what are we supposed to do? You start with Q1. Every one you move on to the right. When there is a 0, again move on to the right. Okay. When there is a 0, you convert it to 1. That is what we did. If x is 2, you move 2 ones, and then the separator 0 comes in between, you convert it to 1 and move further. When there is a blank space, move backward. The first one, you make it to 0 or blank space, whichever you prefer. And then you move till the first character to ensure you get the string. The explanation is given here. This is the diagrammatic representation of what it is. Now, how is it being presented? 1 is the input, X is the content, and then you move on to the right or to the left. So when you represent Q naught is your input state, Q naught is your output state. 1, 1, and R. So that is what is represented here. It is 1, sorry, it is 1, 1, and R. So you have 1, 1, and R over here. Okay. And that is how it has been represented. It is not converted to X. It's 1, 1, and R. It has been represented here. Now, this is for small numbers. Maybe you add a string, add two inputs, you copy an input, you shift it to 2 cells ahead, you shift it to 2 cells behind, you do some bitwise operations. All these are symbol operations. The next comes the complex operation. Now, what do you mean by a complex operation? You have multiple things to work on. Now, this is normally a function f of x comma y. You add it if the x value is greater than y, or you erase the contents of your input cell, that is, you make it to 0 if x is less than y. Now, what all is required over here? I need a decision-making system to check whether the value of x is greater than or less than the value of y. So you have a mechanism to check. What should I use? I have to use a comparer. I have to use a comparison technique to find out the input, which input is greater and which is lesser. Now, if x is greater than or equal to y, you move on and you add the contents of the input. If not, you erase the contents of the input. What do you do? From the left pointer till the end, you make it to 0. Okay, so whenever a Turing machine is asked for any complicated task, you can always have the block diagrams alone. Okay, you need not write a special Turing machine for comparer, a separate one for adder, a separate one for eraser. We know that you can copy a string, you can compare a string, so on and so forth. And therefore, if Turing machine is asked for any complicated task, you can build in the separate components. So for this if condition, you have an comparator which checks x and y, gives the output. Based on the output, you will either have an adder or an eraser. Fine. Hope this part is clear. Now, we'll move on to variations of Turing machine. Before, can I pass? If you have any doubts, you can ask me. Okay, so let me proceed. Then comes the variations of Turing machine. The basic Turing machine, if you are asked to construct, it will be only one among those three which we have discussed so far. The first one is Turing machine as an acceptor, where you talk about A power n, B power n, C power n, and so on and so forth. The next one is Turing machine as a transducer, where we either try to copy the string, erase the string content, add to information, and you might also be asked to subtract two numbers. In that case, we can always ensure that x is always greater than y to make the Turing machine symbol. Okay, so x is always greater than y. For every 1 you have in y, erase 1, 1 in x so that you have some more amount left. Okay, so we will not represent the negative values. And the last one is Turing machine for a complicated task. Now, the existing Turing machine has only one input tape, which is unbound to the left and to the right. Okay, which means you can use any amount of memory to the left, to the right for solving the problem. But in reality, we have a limited amount of memory. But Turing machine assumes unlimited amount of memory, and therefore the input tape is unbound to the left and to the right. Now, there are certain variations of Turing machine, or the modifications of Turing machine, which we'll try to understand only what it is, and then we'll move ahead. The first one is the standard model where you talk about the deterministic model, which we have already used. Okay. You have an infinite tape. You have this read write head. This is the head which we always call it as Q naught, which is indicated by Q naught, Q1, Q2, so on and so forth. So you have a read write head which can move to the left and to the right. Now all the transitions will be stored onto the control unit. You have a list of variations. Okay, so we'll see what it is. Now when I have two different machines, Turing machines, how do I say that two different machines are equivalent? In that case, the language accepted by machine 1 should be the language accepted by machine 2 also, not one string more or one string less. If a machine accepts 10 strings, then M2 should also accept the same 10 strings. In that case, you call it as an equivalent machine. Now you have Turing machine with stay option. What does it mean? If you remember the transitions, whatever we had delta of Q naught, comma 0, for example, and which says either you convert it to Q1, convert it to B, and then you move to the left or to the right, which means I cannot stay in that particular cell. When I read it, you have to move to the left or to the right. Now my question is, if I am reading this A, I am making it as X, and I'm supposed to stay here. Is it possible in the normal standard Turing machine? The answer is no. So what we'll do, we'll take the A, or convert it to X, either move to the right, and next step, you have to retain this A and move to the left so that it points this particular cell. Or you move to the left and the next step you move to the right. So stay option is normally not allowed, whereas here you have a stay option. So the possible options would be L, R, and S, which means I can always say Q naught A, which means Q1, B, and S. What happens? You will have B over here, but then you'll stay in the same position. Fine, that is what they have said here. Okay, that is what they have said here. From Q1 to Q2, you move from A to B, but you stay in the same position. Okay. So stay option machines have the same power as standard Turing machine. That is what we have seen in the previous class. You need not move, but then it will accept all strings by the standard one. And now all these are just the explanations of what we have seen before. So the exam option is stay option machine. If it has to be simulated in the standard machine, it is A to B, you convert it to the left. Then if the left has X, here it is a blank space. If the left has X, you are supposed to retain X and move to the right. That is for in general, for any possible tape symbol you have. Fine. For other transitions, there is no change. If the normal transition says you move to the right, you move to the right. If the normal transition says you move to the left, you move to the left. Okay. So that is what all these steps say. You have option of stay option. Now something has some multiple track tape variant is the second variant what you have in Turing machine. What does it indicate? It indicates multiple tapes which are put together. Fine. So now I'll have a pointer which points to multiple tape inputs of the corresponding cell. If I call it as track 1 and track 2, and if the cell number is 3, in a multiple track tape, I will be pointing to the third cell of track 1, track 2, track 3, 4, 5, how many ever tracks I have. Fine. So you have a single tape and multiple tracks in it or multiple lines in it. where every input is different input. Every track will have different input, but the movement of head is the same. So now what happens? You will have only one head. How do I represent it? It is delta of Q1 of B comma A. You have converted it to CD and you have moved to the left. So how do I represent it? Delta of Q1, this part, it is B and A. So comma, you either have it as B or A in the previous case. Now I'll say B and A within the round brackets, which goes to the Q1 is converted to Q2. So you have Q2, B is converted to D, C is converted to A. So you have C and D, and then it moves to the left. That is what is being said here. Fine. So you have an multiple system, multiple tracking system where you'll be able to do all those informations. So 1 second. That's your multiple track. And next one is a semi-infinite tape. What do you mean by a semi-infinite tape? Semi-infinite tape is bound to one end and it is unbound to the other end. So your initial position is the leftmost cell, which means it is bound to this leftmost position and it is unbound on the right side. Again, this semi-infinite machines have the same power as standard Turing machine. We'll see how it works. Okay, here you have a standard machine where if you have to insert an leftmost indicator to start indicate the start of your input, you will have a special character as hash. Instead of having an hash, further which you will never have any transitions. Okay, so you can have an hash in the between. Now you have semi-infinite tape with two tracks, which is quite easy for us to solve any problem of A power n, B power n. So let me have this information. Suppose if I have to have two A's and two B's in a string, and I have to check equal number of A and B. So you have 2A and 2B. What do? First convert the A to X, move forward, convert the B to Y, move backward, and so on and so forth. So in a semi-infinite tape with two tracks, I'll divide them, I'll fold the tape into half. So the upper tape will have two A's, the bottom tape will have two B's. And since it's a semi-infinite, we'll have the leftmost with the hash symbol, the special character. Now what happens? You will have a pointer which points the first cell of both the tracks. I'll ensure that the first cell has A, first track has A and the second track has B. Move ahead and then check whether the first has A and the second has B. Move ahead, so on and so forth. So what really happens? The way time taken on which you make it to X, walk forward, make it to Y, walking backward, all these are reduced by using a semi-infinite tape, but then it is also capable of solving whatever you have in the other direction. So this is all about this part. Your left part is of the machine is Q1's left and Q2's left and so on and so forth. So here you have AG to right. You have multiple conditions. So you have an X included and then you move to the right. Right? All these are issues with whatever you talk. And then comes the offline machine. So what all we have learned? We have learned about the standard Turing machine, which is the normal Turing machine which we have learned. And then we have gone ahead with multi-track Turing machine. Turing machine with stay option. And then we went in for multiple track Turing machine. And then we had semi-infinite Turing machine. And now comes the offline Turing machine. Now, what is this offline Turing machine? You will have and read only input tape. Turing machine is known for and read write tape. Okay, but here Turing machine will have and read only input tape. The contents are copied onto the tape, which is read write, and you do the work offline, which means it's similar to the assignment which are given to us. You do it, you take up the assignment, you listen to the instructions, go home, go to the hostel, and then solve it. So similarly, you have the input which are being stored. You take it based on the definitions of transition, what you have defined in your control unit. We try to analyze it. So offline machines have the same power. How are we going to do it? You copy the input file to the tape and continue computation as you do in the normal Turing machine. So your standard Turing machine works here. Now what have we done? ABC of your input file is copied onto the ABC of the tape on which we are working offline. Now you will have to work on this tape rather than working on the input file, and then restore back the output onto the input file if required. Okay. Then comes the standard, this is again standard Turing machines which simulate Turing offline machines. So you have and 4 track to keep track of these information. What has happened? This input file and this tape, you make it as a track. Yeah. Now this is your input file ABCD. Your tape content is EFG, right? Your input is ABCD. Now I have to indicate the tape content. If you just look at here, we'll take it as cell 1. 1, 2, 3, and 4. Third cell, I have a pointer which is being pointed. Here we'll take this as cell 1. I'll have this is cell 1. Okay. Cell 1 and 2, I have a pointer which is pointed. Now what happens? I have 2 different tapes where the pointer inputs to points to 2 different cell index. So in order to simulate it, we'll have an 4-track input track tape where the first track will store the contents of the input file. The second track would have the values 0 and 1. Under the cell where you have the pointer, you will have the value 1 over here. Okay, so here C is being pointed and under C you have the value 1. Now what about the tape? Wherever you have the pointer, you have the value 1 in the 4th one. So you have the input file, the head position, the tape, and then the head position again. Okay. Any doubts so far? One second. Okay. Now we'll continue the same concept. Sorry. We'll continue the same set of variants. So you have an offline Turing machine. Now all these hash values indicate the reference point, which says after which or to the left of it, you cannot use or you cannot move ahead to make any transitions. Now there is we talked about multiple track tape, and which is where you use. And next one is second. Yeah. Now you have multiple tape Turing machine where you can have any number of tapes separately, and you will have pointers pointing to different tapes. Now, the pointer which points to tape 1 can point the third cell, whereas the pointer which points to tape 2 can point the fourth cell. That is allowed. That is point number 1. Point number 2, I can do a content change, cell content change in tape 1, and I can retain the content in tape 2. Okay. Then I can move to the left in tape 1, whereas I can move to the right in tape 2. This is allowed because I have two different pointers pointing to two different tapes. It's not one pointer which points to both the tape content. That is multiple track. But here you have multi-tape, where you will have multiple tapes which are point by different pointers for every tape, and tape 1 can move to the left, tape 1 can move to the right. Tape 1 can retain a cell content, whereas tape 2 can change it. Okay. Tape 2's pointer can point to the nth cell, whereas tape 2's pointer can point to a different cell. So how do I? So here you have Q1 pointing to B. Here you have Q1 pointing to the F. What has happened here? If you have Q2, only condition is the states has to be the same. If tape 1 is indicated by Q1, tape 2 should also be indicated by Q2. If the output is getting converted to Q3, then both tape 1 and tape 2 to point to Q3. Okay. So you have here Q1 on A, here it is Q2 on A. Sorry, it is two tapes. Here it is Q1 on B, here it is Q1 on F. So we'll take it as Q1 B comma F. Now on to the output, Q1 has been converted to Q2. Okay, but B has been converted to G and you have moved to the left direction. So G and to the left direction. Whereas F has been converted to D, and the second tape you move the header to the right direction. So BF on GD, it moves to left. First tape moves to left, second tape moves to right. Now this again has the same power as standard Turing machines, which use you can combine 2 or 3 operations under one Turing machine. Now, how are we going to represent it? Again, we are going to represent it in the same fashion. Tape 1 with its head position, wherever the pointer points in, you have a value 1. Tape 2 with the header position, wherever it's been pointed, you have the value 1. Fine. But now, how are we going to do it? Now we'll have a small question which is posted to you. 1 second. I'll have a poll which has been posted, and then we'll move on to the next part. Fine, you have your polls. You have a question and you can start doing it. It is when you solve A per n, B per n using both standard Turing machine and Turing machine with stay option. Both can solve it, but the question is which one is faster, standard or Turing machine with stay option, or both. Okay, let me end the poll. You'll have 5 more seconds to work on. Fine. The answer is Turing machine with stay option. And the reason is, as I told you, first track you'll have a folded concept. So first track, you can have all the A stored in. Second track, you can have all the B stored in. And just say for every A content in the first track, ensure there is a B in the second track. That is more than enough. So that is how it works out. Fine. So that is what has been said here too. Standard Turing machine, sometimes it goes back and forth for A per n, and it takes an order of n square times, whereas in two-tape machine, okay, it's similar to a semi-infinite machine, two-tape machine, it works in order of n. Now, there is something termed as multi-dimensional Turing machine. A normal Turing machine moves to the left, to the right. At the maximum, it has a stay option. But then here you can move up and down. So the complete analysis is based on the XY coordinates. So how will I represent this? How will I represent it? This is in 1, 1. So A and the coordinates need the track given below. So it is A1 for the X coordinate, hash for the separation of X and Y coordinate, and again it's 1, 1. And B is there in 2, minus 1. So 2 hash minus is in 1 acts as a cell content, and then 1 is minus 1, 1 acts as another cell content. And then you have an hash. C talks about minus 1 with 1. So minus 1, there we have stopped our representation, but minus 1 hash, and then you have an 1. Fine. So that is how it works. You will have two different concepts. The last type is the non-deterministic Turing machine. What is non-deterministic Turing machine? For a particular input, you will have more than one output. As here from Q1, if I read A, there are two options. either you convert it to B, move to the left direction, and you move on to a state Q2. And if I have another option where I take C, move to the right direction, and I reach the state Q3. And now, how does it work? Whenever I have multiple options, okay, either you try the first option, doesn't work, you come back, go ahead with the other option, but that doesn't work. So what we'll do is we'll separate them. If I have two options, I'll make it as choice 1 and choice 2. Parallelly compute choice 1 and choice 2 and get the best result out of it. Now, what happens if I have 4 choices? I have to design 4 different Turing machines. It's like designing and working on 4 different Turing machines and coming out with a result. Fine. So, how do I work it out? Mostly, I have all the options of um, taking in and going forward. So if I have 2, you will have 2 tapes, 2 Turing machines. If I have 3 options, you will have 3 Turing machines. Now, how do I refer to the configuration? It is Q0W. That is what we defined in our definition part. On more than one transition, you will have X, QF, and rest of the cell content. Fine. So every deterministic Turing machine is also non-deterministic. So you can try using the same. Fine. So this is all about the computation. You have taken from the initial path, I have 2 options. Okay. And then one option, if I choose, it gets rejected. Second option gets accepted. Last one goes into an infinite loop. So we'll choose the one which gets accepted and we'll say you have obtained the result. Fine. The last one is the deterministic Turing machine. The normal one which we design, which we have designed in our classes, or most probably the deterministic Turing machines. Okay. But then the worst case takes exponential time because you have to work on with all options. Fine. So there we come to an end of variants of Turing machine. If in case you are asked to write about the variants of Turing machine, you can always work on these topics and then pen it down. Okay. We'll have a quick overview on, Turing machine. Now, all this or what I have already I'm not going to work with Turing machine on complex tasks, but then we'll move on to Turing machine, universal Turing machine. Fine, universal Turing machine as such or any finite automata was based on the mechanical means of hardwired way of executing. So mechanical means of executing. And then when you program it, you really hardcore into it. Okay. So you have something called as universal Turing machine. Think of the different inputs you have. You have the tape content, and then you have the contents of the cell. Also, you have the left and right direction to move on. So every Turing machine, what is represented here, delta, so on and so forth, will be represented as 3 different tapes. Okay. So the first one is the description of the Turing machine, which talks about the various states and the transitions. Okay, sorry, the transitions of the Turing machine. And then the tape content, the original content, what we write, rewrite, and work on for getting the output. And the last one is the state of the Turing machine. Now, how do I work on is based on the encoding method. Here you have symbols A, B, C. Now, whenever you do an encoding, you won't have a 0 added. It is all in terms of multiple ones. So I have 4 symbols and therefore I had 1 to represent A, 2 to represent B, so on and so forth. And the next one is state encoding. Again, you have 4 states. You have 1, 2 ones, 3 ones, 4 ones, and so on. For head movement, for left, it is 1 and right, it is 1, 1. Now we'll try to talk about the transition encoding. It is delta of Q1A, which is equal to Q1B and L. Now, how does it get represented? Q1 is represented by 1. So first, the character before the first separator talks about the input state. So this part talks about the input state. And then you have a separator. And then point talks about the input symbol. So you have A, which is represented as 1. And then the separator talks about the transition from input to output. So next followed by the output state. It is Q2, which is represented by 2 1s. And again and separator, the output is B, which is represented by 2 1s. Again and separator, the left is represented by a single 1. So the complete transition is encoded with every parameter separated with a single 0. Now, when I have multiple transitions, what do? Every transition will be separated by 2 zeros. That is what comes here. Every transition is separated by 2 zeros. Fine. So you have the first transition to be encoded and the second transition to be encoded. Fine. So this is how it looks like. Whenever I have multiple transitions, this is how the tape 1 content looks like. Okay. So a Turing machine is a binary string which can be represented by a set of ones and zeros. That is how it works on. Fine. So let us stop here. We have discussed in detail by the way using the variants of Turing machine as well as the universal Turing machine. Turing thesis works in this way. Turing thesis have main points such as you don't have to create any other machines, because as of now, all the known problems can be broken down into solutions which can be solved by Turing machine. Okay. Even if so Turing machine is the most powerful prototype model which helps to solve all problems is known so far. And even if researchers have come up with new models, either they have the power which is similar to Turing machine or lesser than that and not more than that. Fine. So that is your Turing thesis. So we'll stop here. Any further clarifications, you can ask me.